Hello, it's Dave Giles here for the next lesson of Cambridge International Education IGCSE Physics, Unit P4 Electricity and Magnetism. And today we're looking at the first lesson on magnetism, which is basically an introduction to magnetism, where I want you to describe magnetism and magnetic fields, and that does include electromagnets. So, start off by going through some basics, which you'll probably know from Key Stage 3. Magnets, okay, I've got two properties, attraction and repulsion. Uh, they've got no attraction to non-metallic metallic materials, and they attract to some metals but not others. Magnets have the greatest attraction to ferromagnetic materials. So ferromagnetic materials, we've got some metals here, only some of them are ferromagnetic, and if we were to stick them on stick a magnet above them, it would only pick up iron, cobalt, and nickel, because the others are not ferromagnetic. So ferromagnetic materials are ones which contain elements such as iron, nickel, or cobalt. Now, that does include some alloys as well. So if an alloy is a mixture of different metals, if it contains iron, nickel, or cobalt, then it will be attracted to a magnet. And I'm sure you also know magnets have two poles, north and south. And this here is the field around here. So this is what happens if you pour iron filings over an electromagnet, over a permanent magnet in this case. You can see we've got a sort of curvy shape here. And you can see there's a lot of filings as well at these 2 points here, the north and the south end. So why is this happening? Well, it's because you've got you've got a magnetic field around the magnet, and these filings line up along the field, and it shows you the shape of the magnetic field. The reason we've got so many at the two poles, the north and the south end, is just because this is where the magnetic field is the strongest, so that's where there's a lot of attraction for the iron filings. So how will a compass line up with the magnetic field lines of a magnet? So if you put a plotting compass next to a magnet, it might face here. Put it there, it'll face the same direction. Here, it's facing the other way, etc., etc. And if you do this many, many times, and then join up all the points, then you will see the shape of the magnetic field. And a magnetic field goes from north to south, so we can then work out that this here is the north end of the magnet, and this is the south end. So the direction of the field is north to south, and shows the direction of force on a north pole placed at that point. So what that means is if I put a north pole here, then it would be repelled, it would move that direction. Whereas if I put a north pole here, then it will be attracted, it will move towards the south pole. Okay. So where's the magnetic field the strongest? I already mentioned this. You see you get a lot of iron filings at the very ends, and that's because that's the poles, and that is where the magnetism or the magnetic field, is the strongest. You can also tell by looking at the field lines here, the magnetic field lines. Where's closest together, the field is at strongest. So you can see at the poles, the field lines are very, very close together and they're spread out, so it's less strong. So that's one way of seeing how strong a magnet is. Look how close together the field lines are. Again, this is basic stuff you'll have done before, but just to make sure you've got all the knowledge. Like poles repel, unlike poles attract. So you can see here, south and north are attracted, repelled, or south to south or north to north. And you also worth mentioning that magnetism is a non-contact force. And all that means is you don't actually have to physically touch something for the force to be experienced. For example, kicking a football is a contact force. Your ball has to physically make contact, with the ball for it to move. Whereas you can actually hover a magnet slightly above some nails, and it will actually attract them and pick the nails up. And another thing to mention is something like this. So this here is a little sculpture, and it's just tiny little bolts. You put them on, they're all attracted to each other. So if it's all attracted to each other, then that implies that they're all magnetic, which they are. However, these are what's known as an induced magnet. So they're only magnetic when inside a magnetic field. So this here, the base, is a strong magnet. So then it magnetizes this, which then attracts this, which becomes magnetized, which attracts the next one, etc. They lose most or all of their magnetism once they're removed from the field. So if I took away the base, it would all come apart and separate. Here is a past paper question, exam style question rather, which you can have a go at, and I'll put the answers on in a moment. Okay, hopefully you've unpaused it now, and I'll play the answers. Okay, moving on. So we've looked at permanent magnets so far. Now, Cambridge focuses on electromagnets predominantly. So we're going to look today at the basics of electromagnets and their fields. So if you have a wire, and it's just connected to a battery or cell, then you get a current flowing through it, and that current creates a magnetic field. And if you look at it from this direction here, you can see the magnetic field by placing a compass around it, and again, it's deflected, like we said earlier, like if the permanent magnet is deflected. And as you move further away, obviously the field will become a little bit weaker. And that's just me moving it around, showing you the compass in different positions. So you can know which way it travels, so the direction of the field, by looking at the corkscrew rule. So here are some electromagnets, and their shape is just one wire. Now, normally you'll have a lot of turns so that you get a stronger magnetic field that way. So when current is passed through a wire, we get a magnetic field around the wire. In the corkscrew rule, on your right hand, so if you pick up your right hand now, you have your thumb up, and you have it pointing towards your eye, so that means the current is coming towards you. And if you look, you can see the direction of your fingers, which represent the magnetic field. And if you have a look at it coming towards you, so if you've got your right hand and your thumb pointing towards you, then you will see that your fingers are going anti-clockwise. Whereas if you turn it around, you will see your fingers are going in a clockwise direction. So another thing you need to do is investigate how factors which affect the strength of an electromagnet. And one of the most common practicals for that is by picking up paper clips, having some kind of variable, and seeing how many paper clips the electromagnet will pick up when you change that variable. So this here is the example of the circuit. Now, there are different things you can vary. So I'll talk through the circuit first. The circuit is pretty much the same regardless of what you vary. So you've got a power supply, an ammeter to record the current, a switch, not really necessary, but you can put one in there. You have an iron nail, and you have some wire coils. So you have some wire with some turns on it. And the stronger the electromagnet, the more paper clips it will pick up. So there are two ways to investigate it. The first one is you can vary the current. Now, if you're varying the current, what you might do as well is you might also include a variable resistor in here, so you can set the current the way you want it. So you vary the current, and you just see how many paper clips it picks up. And normally what happens is if you double the current, you should double the strength of the magnetic field, which will also double the number of paper clips picked up approximately. You can also vary the number of turns on the coil. So increase number of turns. So you normally wrap a lot of turns around here. The more turns you've got, generally speaking, the more paper clips you'll pick up because the field is stronger. So if you double the number of turns, in theory, you should double the number of paper clips that you pick up. A few things to note, some things that you should keep constant. Make sure all your paper clips are the same weight, same size, because obviously if you've got some which are twice the mass of the other, then you won't be able to compare the results properly. Other than that, depending on what your independent variable is, so for example, if your independent variable is the current, then your dependent variable, your dependent variable is always the number of paper clips picked up, but then one of your control variables would be the number of turns. The other way of looking at it, also the other way of doing the experiment, if you change the number of turns, then you have to make sure you use the same current every single time. And other than that, like I say, make sure your paper clips are the same weight, mass. Make sure you've got a consistent method of picking the paper clips up. Make sure they're unclipped. Make sure, for example, by consistent method, I mean you could just dip the electromagnet into the paper clips and pick them up. You could pick them up. You could do it from one end of the or the other. So from that as well, you can determine from that experiment there's three main ways to increase the strength of an electromagnet. Increase the number of turns, increase the current, and the third method is actually adding the iron core. Now, generally speaking, without the iron core, it doesn't work very well at all. You'd be lucky to pick up one paper clip. So adding the iron core is the best way to increase the strength of electromagnets. However, it's generally considered an electromagnet you would have an iron core in there because they're not very good without them. Last little thing to mention is some practical applications of an electromagnet. So I've got a large one here, which is used for pardon me, which is used at a scrap yard for picking up cars, scrap metal, etc. And one reason we use this is instead of, say, a permanent magnet, is obviously you can release it and pick it up. You can also vary the strength of the electromagnet. So all they'll do is they'll have a control in there where they'll vary the current. And obviously the stronger the current, stronger the magnetic field, and therefore the more metal or the heavier pieces they can pick up. Let's have a look at some example exam questions here. Paper 2. The diagram shows part of a magnetic field around a strong magnet. In which position does a magnetic pole experience the strongest force? It's always going to be at the poles, and the one at the pole is A. Next up, the diagram shows a magnetic field around a conductor which is carrying current. Where's the strength of the field the greatest? Again, it's going to be nearest the area where the current is passing through the wire, and also where the field lines are closest together. And you can see the closest together here. So the answer is again A. The diagram shows the magnetic field of a bar magnet. How does the strength of the magnetic field vary with the position along the dotted path P, R, Q? Okay, so let's go through them from the top. It is consistent along the path P, R, Q. We can see the field lines are, the distance here, for example, is different to the distance here, so that's not true. It is strong at P and reducing strength along the line, the path P, R, Q. Well, the first bit is true. It is strong at P, and at first it reduces in strength, but then it'll start to get stronger as you go from R to Q. It is weakest at P. Again, that's not true. Increase in strength along the path PRQ. Well, at first it reduces, then it increases. That's not true. So hopefully D is correct. It is strongest at P, decreases to a minimum at R, and then increases towards Q. That is correct. So it is that one. At which point is the magnetic field strongest? It's where the lines are close together, so it's A. Which statement about the direction of a magnetic field at a point is correct? So we'll work our way from the bottom. It is the direction of force and a negative charge placed at that point. It's not related to charge, so that also rules out C as well. It's not related to charge, it's related to poles. It is direction of force on the south pole placed at that point. No, it's the north pole, which is what A says. It's the direction of the force on a north pole placed at that point, so the answer is A. And finally, two small compasses are placed closest to a strong bar magnet. In which direction do the compass needles point? So the compass needles will always point towards south. So they are going to be pointing away from north and towards south. So the answer is therefore B. That's it for today's lesson. Hopefully you can now describe magnetism and magnetic fields in both permanent and electromagnets. That's it for now. Thank you very much, and I'll see you later.